Okay, so not so quick. Reminder, 2 weeks already passed. Couple of notions we need to remember in order to understand what I'm going to talk about today. So let's in the beginning. An inner product satisfies three basic properties. Linearity in the first, write it down explicitly. Three row answers. Matrix. First of all, linearity in the first coordinate. A u plus v psi w is a u and w plus n w. The almost symmetry where we change the order of the elements in the product, we get the complex conjugate of the original product. And secondly, the product of two vectors is always greater than 0, and it is 0 and only if the vector itself is the 0 vector. We defined an orthogonal. Still a reminder, let V be an inner product space over a field F. A subset S in V is called orthogonal. Let's write it explicitly with V1 to Vn or something. It's called orthogonal if different vectors give us 0 when we multiply them. The set is called orthogonal if it is orthonormal. If it is orthogonal and the product of a vector with itself is 1. An orthogonal set is always linearly independent. So we can talk about orthogonal bases. And let be V1 to Vn be an orthogonal basis. We know how to calculate the scalars in every linear combination using the vectors of V. And for every V in V, we know that V is the following linear combination, the multiplication or the product, whatever, of V with V1, the multiplication of V with V1 in the denominator, V1 with itself, and multiply it by V1, and so on for every vector till we get to Vn. Let's vector in that. Now calculate the orthogonal, the scalars when the base is orthogonal. When it is orthonormal, the denominators are just one, so it's even simpler. Now, what else? What else? What else? We define the orthogonal space. Blah blah blah. I don't think we need it right now. Hopefully, we don't need it right now. No, we need it. So let's remind you everything we need. B perp perpendicular. Let's do it again. The orthogonal space of set A in V is a perp. That's how we denote it. And it is all the vectors in V such that for every vector V in A, we have the product of V and U is 0. It is always a subspace, blah, blah, blah. We talked about it. Know that for every subspace W of V, we have that the sum of W and W perp is the space itself. What else did we know? Let's put it. Enumeration. Okay. 3, 4, and 5. We define the orthogonal or just the projection. The projection, let W be a subspace of V, and let V1 to, I don't know, VK be an orthogonal basis of W. And the projection of some V in V on W over W, something like that, is defined. We denoted it with pi, as far as I remember. Pi of WV of V is the linear combination from V, but when we take only the vectors of W. We finish here with the index K according to my notation and not with the index N. Now we've already shown the last lecture, lecture number 9, a lot of the nice properties that the projection satisfies. I'm going straight to the links of the lecture number 9 and just copy it from there. I think it will be shorter than write it down one by one. So lecture number 9. What did we say about the projection? I have it right here, right now. We know that out of the box. Bigger font using the PDF. You know what? So instead of W, let's write down U. It's U, still the same. We write it all down explicitly and we proved it one by one in lecture number 9. Okay, along satisfying proof. And we used this concept of projection to prove the previous theory mentioned here. The W plus W is on the vector space. And one last thing, the projection that we proved. That's how we finished lecture number 9. The projection is the same, whatever basis you use. Every subspace is probably infinite number of orthogonal bases, but whatever basis used, you'll get this, of course, the same vector for every W. So let's write down as 6. And the projection of UV is the same no matter what basis, what orthogonal basis of U we use. And that's the last thing we proved in lecture number 9. So all of that, a long reminder, 2 weeks. Last week we didn't have a lecture, so let's make sure we know all the crucial stuff to our next lecture. Any questions about the reminder?
Yeah, can you scroll up for just a sec? I just want to write down the projection formula.
Okay. You want to write it down, so you can argue with him if you want. You want.
No, the project like the formula for projection, like a bit
Yeah.
above.
Some of the class attendees claim that yeah, you have it written down in lecture number 9.
Okay, that's fine.
Okay, so what are we going to do today? It's not the only thing, but we start with it. It's called the Gram-Schmidt algorithm or the Gram-Schmidt process. Of course, Gram and Schmidt are names of long-time dead people. Gram-Schmidt, probably just you write it. Algorithm or process, whatever you want. Okay. The question is simple. In order to find the projection, we need we start with we need to have an orthogonal basis for U. Now, given a subspace, we know how to find a basis. We know from our first course, which is extremely fun, we know that we can express, this is the right word, a subspace of vector space V using one of 3 ways. We can write it down as the span of something. We can write it down with a system of linear equations. All the vectors x, y, z in R3 that satisfies x plus y is 0 or something like that. And we can write it down as the set of solutions to such a system. All the vectors of the form tip, sig 0, something like that. We are given a subspace, no matter how exactly it is written, we know how to find the basis. But the projection isn't satisfied with just the basis. It needs an orthogonal basis. So the question is the following. Given a basis of U, how can we find an orthogonal basis to the same U using the vectors of the given basis, which is not necessarily orthogonal? We know how to find a basis for a given subspace. So the question is that. Question is, given a basis calling B, V1 to Vn of U, how can we use B in order to find an orthogonal basis? Let's call it E with vectors U1 till UN, something like that, of U. Now, the way we do it is called the Gram-Schmidt algorithm. I want to write down how to do it, yeah, the algorithm, and then example, and then we will probably prove why the algorithm is true, but using all the properties of projection that we mentioned here today, it shouldn't be very hard. Okay, so the way to do it, the answer is Gram-Schmidt algorithm. Again, it's Gram and Schmidt, names of deceased people. We're used to it when it comes to math. The answer is Gram-Schmidt algorithm. And it goes as follows. We define, let's write it down with A, B, C, okay? The first vector of E is the same vector as B. Now, the second vector of the should be orthogonal basis is, let's call it U2, just like the band. It is the projection over the span of U1 of the vector V1. No, it's not just projection, excuse me. We take V2, the second old vector, and we subtract the projection of V2 over the span of U1. Explicitly, one can write it down. Let's write it down in a different row, probably bigger. V2 minus the following, and it's projection, right? But it's only one vector, so it is V2 and U1 over U1, U1 multiplied by V2. And then U1, U1. Yeah, of course, that's the projection. It's only V2 there, so it's U1, and it's U1 here as well, of course. And after you have U2, you can move to U3, and U3 is V3, the all the vector, and you should subtract the projection of V3 over the space spanned by the new vectors you've already found, which is explicitly V3 minus the multiplication of V3 with V1, V1, minus the multiplication of V3 with U2, U2.
The projection we said is what the closest combination of the closest we can do to get closest to given vector, right?
Yes.
So they are orthogonal to V3 because V3 is not part of the.
Yes. I mean that's the main claim here.
The main idea.
Yeah.
But it's not trivial.
not so trivial, but using all the properties of the projection, we can prove it, and it shouldn't be very difficult. We'll do it. But first of all, let's finish the algorithm itself. Generally speaking, when you want to calculate, I don't know, UK plus 1, or it's VK plus 1, and you should subtract the projection of VK plus 1 over the span of the vectors you've already found, U1 to UK. It gives you explicitly it, VK plus 1 minus VK plus 1, let's get down to clearly. VK plus 1 with U1, VK plus 1 with U2, blah, blah, blah. Well, let's VK plus 1, UK, UK. And we subtract the projection of the old vector on the space spanned by the new vectors we have already found from the old vector. That's what gives us the new vector. Now, what we claim here is a double claim. First of all, I claim that it is a basis for the same subspace. It is not very hard to see. I mean, it's the same vectors, V2, V1, blah, blah, blah. And secondly, is more important, the new vectors, U1 till UN, are an orthogonal basis. Not just a basis, but orthogonal. And if one wants an orthonormal basis, well, he can normalize each vector here of the U's. But before we prove it, it's a big formula. I mean, it's not the most terrifying mathematical formula ever, of course. And we can write it down pretty easily with a sigma. But yeah, it's multiplications, denominators, numerators, minus, plus, blah, 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 pi, span. Let's go for a nice example, and then we can move on to the proof. Have some notes about this algorithm. For example, so be not afraid. Schmidt is dark and full of terrors, but using an example, it shouldn't be very terrifying. Okay, an example. I don't want to do it very simple, but I don't want to do it very exhausting. I mean, look at R6 or something, but it take us forever. Let's have R4. Okay. And let's already start with some bases. Hopefully it is a basis. And the vectors are really linearly independent. 1, 2, 3, 4. Yeah, let's do 1, 0, 1, 0. And 0, 1, 1, 1. Notice that they are not orthogonal. The multiplication, the standard inner product, gives us 1 as far as I can see. And someone else.
Right, not to put 0, 1, 0, because wait, no.
Yeah, let's do 1, 3, 4. Hopefully it is a basis. I mean, we can check it, but let's trust ourselves. Yeah, it is a basis. Notice that in these two vectors, the second and the fourth coordinate should always be the same. So as long as we take here different coordinates, something like that, it should.
How can it be a basis if there's only 3 vectors in the pattern?
It's a basis of a subspace, not the subspace itself, not the space itself.
Oh, okay.
Yeah. I
Right,
mean,
right.
for the space itself, for here in our example, R4 itself, we can talk about the standard basis. One with everything else is zero, and it should be fine. It's an orthonormal basis. But for a subspace, we are given, or at least we can find a basis. How do we find an orthogonal basis? So here Gram-Schmidt comes to, in Hebrew, say, "לעזת חבר," to help a friend. In order to have the same notation as the general description of the process, let's denote our vectors with v1, v2, v3, okay? Not very important. And moreover, one can denote v1, v2, v3 in whatever order he wants. I mean, if you think that it is pretty easier, but the calculations are easier when you start with 1, 3, 1, 2, or 3, and not with 1, 0, 1, 0, you can do it. It's fine. It's a set. It doesn't have any specific order in it. Now, by our algorithm, forgot to fill up my bottle before we start. I'll make do. A break. Now, first of all, U1 is V1, which is 1, 0, 1, 0. Secondly, then after you have U1, which is V1, yeah, you can write down V2 minus the projection, which is U2. And specifically in our case, the second vector is 0, 1, 1, 1, 1 minus the finest product one can find, 0, 1, 1, 1, 1. U1 is 1, 0, 1, 0. And U111 is yet again 1, 0, 1, 0 multiplied by itself. And 1, 0, 1, 0. We already know if the inner product isn't explicitly mentioned, it is the standard one. First coordinate plus second plus third, etc., etc. What do we actually have here? The multiplication, let's write down explicitly. I'm not rushing to anywhere. We have EP2 afterwards, right? So it is 0 multiplied by 1 plus 1 multiplied by 0 plus 1 multiplied by 1 plus 1 multiplied by 0. It is almost 0, but it isn't. I write down explicitly afterwards, part of the notes I want to note. If the vectors are already orthogonal, Gram-Schmidt will not screw it up. It will maintain the same vectors, only the not orthogonal vectors will be changed. Moreover, if it is not a basis, or if the subset is linearly dependent, Gram-Schmidt will get rid, just make them zero there, get rid of the unnecessary vectors, but not now. Let's finish our example. So it is 1. All this fancy.
Sorry, are
Well,
you sure the photo one is correct?
No, I'm not sure because I copy and paste it.
Yeah.
But it is not the same product. You are right. It's 1, 1, 0, 0, 1, 1, 0, 0. So it is 2 and not 1. You are correct.
Data product of vector set is never zero, the
No.
vector is zero, right?
Yes. Moreover, it is always positive.
Yeah.
So it's 1 above 2. No, for when it comes to a product, it's always positive, whatever the field is. Now, yeah, but the standard inner product over the field of complex number is U multiplied by its conjugate.
Oh.
Okay? So you do end up with a positive number. Okay. minus half. What can men do against such reckless fractions? We have, you can put the half outside if you want, right? The scalar, but then you should multiply it by 2 before you subtract. So it is minus 1 and 2 and 1 and 2.
Can always use the previous part of the algorithm to help us on the next parts.
It's not just we can use, we have to use it.
No, I mean,
Iterative.
outside of the, we need to use two, we can just copy the part of U1, I know, because the inner product with the next vector.
Yes, it's not just you want multiplied by scalar, it's some subtraction, which gets uglier and uglier as it goes. Yeah. So hopefully I wasn't mistaken here when I took the half and then subtract the vectors from each other. Minus 1, 2, 1, 2. Okay, that's the second vector. Now, one can always check himself before he wrecks himself, right? Does the new vectors are orthogonal? Now, by looking at it, the answer is yes. You multiply the 1, 0, 1, 0 with the minus 1, 2, 1, 2, it is 0. So we can say that we are correct here, but it's not just, as I mentioned before, and we'll prove it later on. It's not just the new set is orthogonal. It has the same span as the original set. So it is not so clear, but this is how we use the algorithm. First of all, example. And then after we have the second new vector, this is U2, we can calculate U3. And here I stop because we have 3 vectors in the original set. We will have 3 vectors in the new one. But it can go as far as you need. It's pretty technical and boring. So without any promising something, but in the test, more than 3 vectors in Gram-Schmidt. Not saying it's not going to happen, but the probability is close to 0. Okay. Just because it's long, it's not something hard or difficult. Okay, using our specific vectors, we have P3 is 1, 2, 0, 3. Minus the multiplication with U1, but just for V3, not for V2. And the multiplication of V3 with U2. So U2, we have already found it. It's this nice half vector. So it's all U2, 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 U2. Okay. And now notice something nice from the technical point of view. We're having a U2 and I wrote it down with a scalar outside. The scalar cancels itself when we look at the product. I mean, it appears 2 times in the denominator and 2 times in the numerator. So we are left with no scalars at all, which is nice. And whatever the scalar is, we can delete it, cancel it. Notice that, generally speaking, when we have a scalar in the second coordinate of the product, when it goes out with a complex conjugate. And we cannot always say, the scalar just cancels out, and that's all. But when it comes to real numbers, it does happen. So when we getting into calculating the products themselves, what do we have here? I write down explicitly with the products, okay, but if you are on the final exam, running out of time, and you write it down very quick, it's totally fine. I don't need to show me how you multiplying 0 with 1 and then add it to 0 multiplied by 1, etc., etc. Now it is 1 multiplied by 1 plus 2 multiplied by 0 plus 0 multiplied by 1 plus 3 multiplied by 0. And on the denominator is the same. Okay, okay. Now, what do we have here? Yet again, the scalar half cancels out. We are left with 1 multiplied by minus 1 plus 2 multiplied by 2 plus 0 multiplied by 1 plus 3 multiplied by 2. And downstairs, minus 1 multiplied by minus 1 plus 2 multiplied by 2 plus 1 multiplied by 1 plus 2 multiplied by 2. All that multiplied by our vector minus 1, 2, 1, 2. Okay. Now, what do we have here? Here we have 1 above 2. It is yet again half. Here, it is minus 1 plus 4 plus 6. It is 9. And here, 1 plus 4, 1 plus 4. By Allah, I think it is 10. Correct me. As much as needed. Is the page up. First page up. Now it's so close to the control, which is the main button I use when I write it leaks, and my fat, slow old fingers push it sometimes. Okay. What do we have here? Let's write it down as with 10 in the denominator. So it is 10 minus 5 plus 9. I think it is 14. If I'm wrong, please correct me. 2 becomes 20 minus 0 minus 18. It is 2. 0 is 0 minus 5 minus 9. It is minus 14. And for my last trick, 3 is 30 minus 0 minus 18. It is 12. Now the question is, we can check it out. Is it really orthogonal to the previous two vectors we've already found? As far as I can see, as I calculated in my head, it is. Now the scalar doesn't change anything, doesn't change. It's only about the vectors themselves. And they do give us 0 when we multiply it. So by Allah, by Graham Schmidt, the set of U1, U3, U that we got here is an orthogonal basis for the U we start with this spanning set, with this basis. One can check that it is orthogonal, and one can say, you know what, scalars doesn't change anything when it comes to linear dependency and to spanning set, so we can give up on the scalars and it will be totally fine. Yet again, is probably an infinite number of orthogonal bases for the same U. When it comes to orthonormal bases, we need the vectors to be with norma equals 1. With norm equals 1, it is not so trivial. So when it comes to orthonormal bases, maybe there is a finite number of such vectors, maybe not. Don't want to go from at least right now. into this dark corner, counting bases. Okay, this is the process. It is very boring, very technical. We just have to do it in caution because it is long, many multiplication, many indexes. It shouldn't be hard, but it can be confusing. Any questions about our process? Okay, so as I mentioned, I want to prove it, and I want to note some notes about the algorithm. Okay, so let's start. You know what? Let's start with the proof. Yeah, that's I want. Or probably with no. Let's start with the notes and then the proof. Notes. First of all, if we want or need an orthonormal basis, not just orthogonal, we use Gram-Schmidt, and then we normalize with two L's, whatever. As long as you can understand me, it's fine. And normalize the vectors. Normalize is dividing each vector with its own normal, by its own normal. Yeah. And in the orthonormal set should be the vector u1 divided by its norm, and u2 divided by its norm, and so on. One can, and when I use the Gram-Schmidt process, the algorithm, I actually do it. One can normalize the vectors in every step of the process. I mean, you get here u1 is v1, so normalize it. The actual u vector is v1 normalized. Then you have u2, and you will normalize it and using the normalized vector or vectors to the next steps. Not necessary, but one can do it.
That's zero, right? Because when you divide by the multiplication of a normal vector with itself, it's one.
Yes. When you normalize the vectors at each step, the denominators here are all one. On the other hand, you are multiplying the new vector, the old vector, with your new vectors, which are now orthogonal and can carry with them some ugly scalars outside. In order to make the norm equals one, it is probably the same complexity, however you do it. Let's write down explicitly. Moreover, we can normalize the vectors vk, vk with every step, or in every step in the algorithm, whatever. Okay, this is the one thing I wanted to note when we talk about orthonormal. The difference between orthogonal and orthonormal is easier to, the gap between them is easier to close. Secondly, if as I mentioned, if we already start, if the vectors are already orthogonal, Gram-Schmidt process will not change them. There are different orthogonal bases, but the process will write the same. I mean, we are calculating these products, and all these products in the numerators are zero because the vectors are already orthogonal. So we just stay with the same v1, v2, etc. vectors. What else? We can say, and probably we'll see it through the proof. We claim that no, please. I know it's out, but it's the why are you so why so hot? We claim that the subspace spanned by the all vectors v1 to vn is the same as the subspace spanned by the new ones, right? But using our process, we get something even stronger. We get that this is the claim, I want to prove it, but I can say something even stronger. Moreover, it is even stronger than that. For every k, we have that the space spanned by the k new vectors is the same as the space spanned by the k old one. And we can see it from the algorithm. The first vector is the same first vector. Now the two first vectors, u1 and u2, actually span the same as v1 and v2 because it is a linear combination of v1 and v2. So it's not just, the finish line, we get the same spaces, but in every step in the algorithm, we get the same space. The k new vectors and the k old one span the same space. Okay. Now, what can we do here? I have another one thing I want to say here about the notes. But let's firstly prove Gram-Schmidt algorithm, and then why is it true? Yeah, and then we can move on. Any questions about the notes I just wrote here?
Oh,
What?
so every that's time.
Yeah.
Say,
Yes.
how do you define the order of the stands? And because then you want basic.
Yes, I'm starting with the basis. I can choose whatever order I want to start with, but I choose an order and I work with it. I'm writing down. This is V1, V2, V3, etc. Okay. Let's prove why a Gram-Schmidt is true. And yet again, we actually claim here two things. We claim that, first of all, the set of the new vectors is orthogonal. And secondly, has the same span as the old set. Now, for the first وكليم for the first part, why the new set is orthogonal, we use this property of the projection. Now, by definition, what is the vector vk plus 1? It is the vector vk plus uk plus 1, the new one. Is the vector vk plus 1? Ah, here is a mistake. It is the projection of vk plus 1. So I write down explicitly here. We subtract the projection of vk plus 1 from vk plus 1. By our definition, this vector is in the perpendicular space of the space itself. So now, let's write it down explicitly. Yeah, but every vector added is orthogonal to all the vectors that are already there.
We don't have to prove that like being orthogonal to all the last ones and orthogonal to all the next ones. It's orthogonal like this, like trivial.
No, I'm saying let's put it that way. This is the new vector, right? So one can think of it as an inductive process. I mean, first of all, U2 is orthogonal to U1. And then I want to prove that when we have a set of k orthogonal vectors and we add the k plus 1 vector, that in this way, it is orthogonal to all of them. This is uk plus 1. Write down explicitly. This is uk plus 1. We can think of this as again, as proved by induction if you want, but don't need to write it down that way. We need to show why u plus 1 is, you know what? Let's write it down explicitly. First of all, u2 is minus the is v2 minus the pi of span of u1 on u1 or over u1 of v2 by the property where is it? This one? That v minus pi uv is always in u perp, we have that u2 is in the perpendicular space, the orthogonal space of the span of u1. It is the specific u here, which means that u2 is orthogonal to every vector in the span of u1, including u1 itself. So you can think of it as well as write down explicitly, u1 and u2 are or is as a set orthogonal. Vectors are orthogonal. Now, by induction, assume that we already have the set of first k vectors is orthogonal. What? Yeah. Unlike when people come in, she didn't run away, right? Let her be. Let her be. Assume that the set U1 to UK is orthogonal, and we need to prove that the set U1 till UK plus 1 is orthogonal, and by induction, we prove our claim. The vectors U1 to UK are, by our assumption, already orthogonal, so what is left to prove? And to show that the vector UK plus 1 is orthogonal to the vectors U1 to UK. Now, indeed, the vector UK plus 1 is VK, blah, 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 blah. So by the property number 4 of the projection, as we already proved 2 weeks ago, we know that UK plus 1 is in the orthogonal space of the space we project on, which is the span of the orthogonal space of the span. Oh, here it is. Here's Birdie. Of U1 to UK, and by the definition of orthogonal space, UK plus 1 is orthogonal to every vector in the span, specifically for UK to U1 to UK. And first for for I is 1 to okay. Now it's little spaces here. Is the elix thing just write down, as you know. Now let's write down mathematically from left to right for every for all I between 1K. So Gram-Schmidt, first of all, gives us an orthogonal set. Now, for the second part of the proof, we need to show or to explain why it is spanning the same set, the same space as the original set. Any questions about proof number 1? So for number 2, we need to show it's the same, but as we mentioned here in the notes, we can prove something even stronger. It's not just in the final line, the bottom line, that the finish line. It's the same space. It's the same space for every step you take in the algorithm. Let's write down explicitly. U1, it is V1. So they have the same span. Now, U2 it's the vector right here, but we know that U1 is actually V1 by the first step of our algorithm. So it is, this is U2. No, it's not good. So U1 and U2 are both linear combinations of V1 and V2. U1 is actually V1, and U2 is some linear combination of V1 and V2. We can write it down. We can say that U1 and U2 are in the space of the space spanned by V1 and V2. But on the other hand, we have already proved that the set U1, U2 is orthogonal. Thus, as already mentioned, it is linearly independent. We have a space spanned by two vectors on one hand. And on the other hand, we have a set of two linearly independent vectors. By errors, I called it, we already mentioned it in some lecture before, hashlishi hinam in Hebrew. How do we call it in English? Huh?
We said 2 plus 1.
2 plus 1. This is very good. 2 plus 1. We have a set of 2, which is the dimension of this space, because it's spanned by two vectors. Linearly dependent vectors, it must be a spanning set, must be a basis. It is a linearly independent set of two vectors in a space spanned by two vectors. This is the span I talk about. So it is, hence, I use some fancy words like that. Hence it is spanning set. So indeed, the space of the span, the subspace spanned by U1, U2 is actually the same as the span of V1, V2. But one can do this process over and over again. I mean, looking at U3 in the process, U3 is a linear combination of V3 and U1 and U2, but U1 and U2 are already linear combinations of V1 and V2. So at the end, U3 is a linear combination of V1, V2, V2, V3. But on the other hand, U1, U2, U3 is a linearly independent set, so it must be a spanning set as well, and so on and so on. And in general, U k plus 1 and all the other new vectors are all linear combinations of V to V k plus 1. So the vectors U k plus 1 to U1 are in the space spanned by vk to vk plus 1. And on the other hand, the set of uk plus 1 till u1 is linearly, I missed the A here, linearly independent, because it is orthogonal. We already proved that. And so the span should be the same. So yet again, it's not just for all the subspace, all the subspace spanned by all the vectors u1 to un is the same as the subspace spanned by the vectors v1 to vn. For every step, it is true. The span of the k vectors, k plus 1, whatever, new vectors we've already found is the same as the span of the k alt vectors we already have.
Can I ask a question?
Yeah, of course.
Does this mean that there's for every basis there's a unique linear transformation that can transform the basis to an orthogonal basis?
If you start with the basis and you determine the order of the vectors in the basis, then you use the Gram-Schmidt method, algorithm, process, whatever, you will always end with the same orthogonal set. But first of all, one can take the vectors in B in a different order and then try to calculate the orthogonal base you get from Gram-Schmidt. It will be probably something else. And moreover, one can mathematically start with a different basis of U. When we have, in our example, for example, with this basis. I mean, we can add these two vectors up and get 1, 3, 1, 4, and use it as a vector of a basis instead of 1, 0, 1, 1, 1, for example. Then you use a different basis to begin with, you will finish with a different orthogonal basis. That's for sure. Okay. Any other questions about that?
But you can use a linear transformation to map it, right?
Can you use what?
A linear transformation to map it.
Yes, we can.
Okay.
Okay. You know what? We get to the time where we usually take a break, so we can't take a break here. I wanted to note one last thing about this orthogonal branching, etc. And then we'll from the break, we'll talk about some of the basic inequalities. Like we already mentioned Pythagoras, but some other basic inequalities of inner product spaces. And then we can move on. Let's see how much and how will we do it. Okay, let's take a break. I'm pausing recording. Blah blah blah. Okay, I wanted to say just as I mentioned on another thing, another note before we move on. Note, given let write that nicely. V be an inner product space over a field F. Page up, as I already mentioned. And let, I don't know, V1 to Vk be an orthogonal set. We can always complete, that's the right word, right word, complete the set to an orthogonal basis of the space V. To V1 to Vk, but then some Vk plus 1, Vk plus 2, and so on. Do we get a Vn or something like that? Where the set of the new vectors, Vk plus 1 to Vn, is a basis for an orthogonal basis, is an orthogonal basis for the orthogonal space of the other original all vectors. Now, technically speaking, we know from linear algebra 1, which was extremely fun, given an linearly independent set, we can add vectors. Doesn't matter how specifically we do it, technically speaking. We can add vectors to the set till it becomes a spanning set, but it's still linearly independent, which means it is a basis. We can do it. What I actually say now, we can do it with orthogonal basis as well. We started with an orthogonal set. We can add vectors that on one hand gives us eventually spanning set, and on the other hand, the new set is still orthogonal. Technically speaking, one can, first of all, complete the set V1 to Vk to a basis. Don't know how exactly Iris explained linear algebra on how to do it. For example, one can take the vectors, put them in the rows of matrix, eliminate whatever can be eliminated, and then add vectors with one in every column without any pivot element. And then it will be linearly independent with the old vectors. And then when you have a basis, you can apply Gram-Schmidt in order to achieve an orthogonal basis. So this is why I note it here. I mean, we've already defined the notion of orthogonal basis, as far as I can remember, 3 weeks ago. Could have already said it there. Maybe I've already said it, but now after Gram-Schmidt, one can also do it, technically speaking, finding an actual orthogonal basis for every subspace or space you want. Okay. Any questions about my note? Okay. I'm going to use this note with the following theorem, and let's write it down. The fundamental, yeah. So write it. What? No, it is linearly independent.
But it's not necessarily spanning.
Exactly. The fundamental inequalities of inner product now, we have already mentioned that the projection is the closest vector to V in U, which means that the norm of the space is whatever it is. Don't think I need it explicitly in my new inequalities, so I'll just write them down, but notice that it's not something completely new. We've already talked about inequality. Just a second, something here is weird. You watch it perfectly, but something on my screen, it is claiming that I somehow run over it. So right now, it will be fine again from your and mine point of view. Okay, fundamental in a product. Let B be in, you know what? It's right down here. Let V some vector in V. Now, first inequality is called the Bessel inequality. It's the name of a guy, a deceased dude. And let's write down with two S's. Yes, it's Bessel with two. What? What'd you say? Bessel, yeah. Friedrich Bessel. He's been dead for something like 180 years, something like that. This Bessel, in gram, which means already I wrote that. Bessel inequality. If the set V1 to Vk is not just an orthogonal set, but it's orthonormal, then the norm of the vector squared is greater than the absolute values squared of the more products of V with V1 and V with V2, so on, so on. And when we do have an equality, an equation, and we have an equation if and only if the vector is in the span of the set. Is Bessel, we will prove it. And my second one is called Cauchy Schwarz. Cauchy, in Hebrew, Cauchy is difficult. Yeah. So I used to, I always say that every theorem is Cauchy for us, but this specific one is called Cauchy. But how do you write his name? I think it's that Cauchy. Schwarz. May the Schwarz be with you. Schwarz with Z. I think it's with Z. Cauchy Schwarz. He says that without specifically talking about an orthogonal set, you know what? So I'll rephrase it. We have an inner product set, inner product space. Okay, now we don't need this one. I just want you to look at V and U in V. And here I will say that if the set is orthonormal, then blah, blah, blah. And secondly, Cauchy-Schwarz states that the absolute value of the inner product of U and V is always smaller than the multiplication of the norms of the vector. And when do we have an equation? The product, the multiplication of the norms equals the absolute value of the inner product. If you don't leave, the vectors U and V are linearly dependent. This is our Cauchy-Schwarz inequality. And the third one is the triangle inequality. We have an inner product. We know that the inner product induces our norm. And then we know that the norm of U plus V is smaller than norm of U and the norm of V. In other words, the square roots of the inner product of U plus V with itself is smaller than the sum of the square roots of the inner product of U and the inner product of V with itself. Now, we've already mentioned it when we discussed the notion of norm, but we didn't prove. Why is that so? Now, when we have the Cauchy-Schwarz, we can use it to prove our triangle inequality for the norm induced by the inner product. So we have three inequalities. In addition to the inequality about the projection. And I want to prove them. I want to prove all these inequalities. Let's see how much time is left. We can start on the next subject. It's still talking about inner products. Etc. Any questions about the theorems themselves?
I don't think I have any information for that.
No, it's very not intuitive. I mean, when we talk about R2, we can probably give some, R3 geometric interpretation for that, but generally speaking, it is difficult. Okay, let's prove them one by one. Take them out one by one. So first of all, for Bessel, we have an orthonormal set. And we need to show that norm of V is greater than that. That happened here. What? Where's my? What? As we've already mentioned, we can complete the set to an orthonormal basis of V. Get up the following vectors. Vk plus 1, and so on to some Vn or whatever. As we already mentioned in the note we took before we wrote the inequalities, given an orthogonal subset, we can complete it to an orthogonal basis. Now, the difference between the gap between orthogonal and orthonormal is not very hard to close. Just normalize each vector, so we can already say that given an orthonormal set, we can complete it to an orthonormal basis. Now, we know that the vector V can be described as the following linear combination: V multiplied by V1, V1, plus V multiplied by V2, V2, and so on. These are the scalars in the linear combination, as already shown 3 weeks ago. 3, 4, I don't know. Time is running when you like. It is K, and so on. Yeah, goes to K plus 1. And finish with N. What happens when we look at the norm squared? The vectors in the linear combination are orthonormal, which means that they are orthogonal, and so they satisfy Pythagoras Pythagoras theorem conditions. What Pythagoras says: if two vectors W1 and W2, should have mentioned it before, W2 are orthogonal, then the norm squared of the sum is the sum of the squared norms. So what do we have here? The square norm of V is the square norm of all the beautiful things. Now the vectors are orthogonal, so by Pythagoras, the norm squared of the sum is the sum of the squared norms, so it is this one and that one. And with K plus 1. So what do we have here? Now, don't get distracted by the letters. V, psic V1, V, Vk, the products are scalars. So we know how to pull out scalars from the norm. We pull them out with, let's write it down explicitly. Now, I want to delete all of it. Now, we know that the norm of A with W is the absolute value of A multiplied by W. And it is easy to prove using the explicit way of writing down the induced norm with as the inner product of vector with itself. And so we can take out the V with V1 in an absolute value. Of course, it is squared because the norm is squared, multiplied by the norm of V1 squared. And it goes the same for all the others, all the other kids, all the other multiplications here. Vk with Vk, and Vk plus 1 with the Vk plus 1. And so on, for Vn. The set is orthonormal, not just orthogonal. So each norm here equals 1. And we are left with the norm of V squared, where we began our journey, equals the sum of all the absolute values of the inner products squared. If I give up on all the additional vectors we added in the beginning of the proof, I'm giving up here on non-negative elements, which leads to a smaller expression. So this is the big main claim of Bessel, that the norm of B squared is always greater than this sum. But as I've already said, Bessel says another thing. He says that when V is in the space spanned by V1 to Vk, it equals this sum here. And now, moreover, if V is in the span, V is in the span, what the hell? Third time, V is in the span of V1 to Vk, then V is, or then V is in, as we already mentioned, in the way of completing a base to a orthogonal base, is in this orthogonal space of the space spanned by the rest of the vectors in the bases. So all these multiplications are just zeros. Because the multiplications of V1 with Vk plus 1 and Vk plus 2 and blah, blah, blah until Vn is just 0. So we do have an equality. When V is already spanned by V1 to Vk, is in a correlation of V1 to Vk, then all these are not just greater than 0. One can write it down that way if you want. They are 0. So it is an equality. Okay. This is the proof of Bessel. The equality is called Bessel equality. But it is a specific case of the inequality. So that's how I write down. Any questions about our proof? Mm-hmm. Okay, so our next theorem was Cauchy-Schwarz, right? So let's prove Cauchy-Schwarz. Will be 2. We'll have a Cauchy Schwarz. We need to show that the absolute value of the product is smaller than the product of the norms, and then we show that it is equal when we have when the U and V are linearly dependent. First of all, it is easier to see that when U and V are both 0, both sides are 0. So it do happen, it does happen. Now for my second proof, I'm trying to use Bessel inequality in order to prove Cauchy-Schwarz inequality. Now assume that U isn't 0 or V isn't 0. We can assume that, let's say V is not 0, the proof for U is not 0 is same, just switch the letters. What does it mean? V is not 0, so we can normalize it. Looking at V above T group. The norm of V, and we can look at the set of V, the normalized V, and that's all. It's a bit boring, but by definition, it is an orthonormal set. It's only one vector, so it doesn't have to be 0 and multiplied by something, and it is of norm 1 because it is normalized. The set is orthonormal. Meaning that we can use, no meaning, so we can use Bessel inequality over this set. I'm looking at the vector U, and the norm of the vector U is squared is greater than the squared absolute values of the multiplication or the product of U and the vectors of the orthonormal set. Now, the orthonormal set contains only one vector, so we're going to have only one element on the other side. What? Get out. U with the normalized V. Now, squared. We know that V is multiplied here by the scalar one above the norm of V, and we know how to put out scalar from an inner product. Notice that the scalar here is on the or in the second coordinate, so exactly by our cautious rules, it is the conjugate of 1 above V. But we know that a norm, whatever the vector is always a real number. We know that one of the norms properties, basic properties actually define it. We know that V is in R. It's true for every vector, so we have oh, okay. We can delete conflict. And we are squaring multiplication, so it is actually squaring each one of the friends here. Multiply each side by the norm of V squared, multiplying multiply by the norm of V squared. Get the norm of U squared multiplied by the norm of V squared is greater or equals the absolute value of the product between U and V squared. And of course, we can look at the square root of each side. We are given our goal. And why does inequality hold when the vectors are linearly dependent? Moreover, or furthermore, if you want so, or in addition, by Bessel, we know that quality holds when U is in the span of V above the the norm of V which means that U is some scalar multiplied by this vector. That is equivalent to U and V being linearly because one is multiplication by some scalar. Of the other. So Cauchy Schwarz hold as well.
What if the quantifier over the normal V? What number the normal V?
Because the norm of v is always a real number. And the conjugate, coupled conjugate of a real number is just the number itself.
Oh, it's the same from Schmidt, right?
Yeah. Any other question? Okay, so third inequality is the triangle one. Triangle. We need to show that the norm of u plus v is smaller than the norm of u plus the norm of v. Okay. The norm of u plus v, let's look at the norm squared, all right? Then we'll look at the square root in the end. The norm is squared is the multiplication of the vector with itself. Because the norm is the square root of the multiplication of vector with itself. We know how to write it as a sum of inner products using the property of linearity of inner product. We have the four products here actually. It's u with v. It's u. Let's write down that way. It's u with u. It's u with v. It is v with u. And it is v with v. Now, what can we say about each and every element of this sum? First of all, u with u is the norm of u squared. And v with v is the norm of v squared. But what about v and u and v? What can we say about them?
They are equal.
They're not equal. It's a bit different. We can write down v and u as the complex conjugate of u and v. So we have here u and v. And the complex conjugate of u and v. Overline. And the norm of v squared. Now, what happens when you add up a number with its complex conjugate? What are you left with?
Imaginary part? No.
No.
The real part.
The real part, and actually twice, right? If you Let's write it explicitly. We know that some, I don't know, W plus over line W. Let's see if you can see it right here. So I'll write down explicitly with over set and a very visible line. W plus W, it is A plus BI plus A plus BI conjugate, and it is A minus BI. So just 2A, which is twice the real part of W. But I want you to notice that the real part of W is always smaller than the absolute value of W. Why is that? The real part of W is the, I mean, it can be positive, right? If you put it in, if you want. Absolute value. The absolute value of W is the square root of the real part squared and the imaginary part squared. Then, I don't know. Why aren't you going to sleep? Why are you tired? Wake up. What have you done today? But you're already tired. It is the square root of the real and the, so one can write it down as, let's write it down a bit differently. Very explicit. This is the absolute value of real W. As always, the absolute value of a number is greater or equals the number itself. Now, the absolute value of a number is the square root of its squared value. And t is smaller than the square root with the additional imaginary part, which is the absolute value of W. So what do we have here? Is it enough? Yes. So we are the world, we are the children. Here, the number U, the product UV with its own conjugate complex are the real 2 times the real of the product, and the real part is always smaller than the absolute value. Now, how convenient. Step by step, we used Bessel in order to, we used Pythagoras from last lecture to prove Bessel, we used Bessel to prove Cauchy-Schwarz, and now we use Cauchy-Schwarz to prove the triangle inequality. We know that the absolute value of U, the product of U and V, is less or equals the multiplication of the norms of the vectors. So now, I don't need this little red arrow here. By Cauchy and Schwarz. This one here is greater than then this one here. Have norm of u plus v squared, which is norm of u squared, 2 times the value of the product, and the norm of v squared is smaller or equal. The following sum, we substitute the absolute value of u with v with the multiplication of norms. We know that this is the norm of u and the norm of v squared. So, oh, and indeed, u1, the norm of u plus v, take the square root of each side, of course, is equal or smaller than the norm of u plus the norm of v. Now, as already mentioned, when the vectors u and v are linearly dependent, the equation holds. Because it holds in Cauchy-Schwarz when they are linearly dependent. Sorry. Any questions? Okay, we have just another one little thing to talk about today. We can finish and get ready for Infi 2. This one little thing is called the Gram matrix. I'll write it down, and the theorem about it without the proof is also going to use it if it needs to be. Let f the v blah blah blah. Let's copy it from somewhere else. Now we have some basis. It's not necessarily orthogonal nor orthonormal. Let b with v1 to vn be an ordered. The order is important. V1 is the first, V2 is the second, etc. Ordered basis of V. The Gram matrix of V is defined by, first of all, it is denoted by GB or something like that. Sammy, you're from GB, aren't you? UK, GB, every lecture we find you.
Woo!
Yes. Union Jack flying in the background. Yeah.
Yeah. Order in this case has no inherent meaning, it's just like we have V1.
Yes. Yeah. I mean, look at the matrix. G is denoted GB. Let's write it down. Oh, nicely. Is denoted GB and is defined by what is the ij element of GB? The element of IGB is the inner product of VI and VJ, the vectors from the basis. Now notice that, for example, let's read it quickly. For example, in V, which is R2, and basis with, I don't know, 1, 0, and 1, 1. We get that the matrix GB has 4 elements. It is a matrix order n on n. Here it is the multiplication of 1, 0 with itself. And here is the multiplication of 1, 0 with the 1, 1. And here it's vice versa, 1, 1, 1, 0. You see 1, 1, 1. And assuming it is the standard inner product as ways, we are having here 1. This is 1 as well, 1 as well, and it is 2. 1 multiplied by 1 plus 1 multiplied by 1. This is the ground matrix. Notice that the matrix here is I, meaning all the products of vector with itself is 1, the products of vector with another vector are 0, if and only if, probably practically by definition, B is orthonormal. And one can say that the Gram matrix is diagonal if and only if the basis is orthogonal. Our main and only theorem about the Gram matrix is the following theorem. Let's write it down and we can finish. Not, of course, I'm planning on proving it today, but I don't think we're going to prove it next week either, or any other of the weeks left of the semester. Theorem, let blah, 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 blah. Okay. And let U and V be some vectors in V. Then one can write the inner product between two random vectors U and V using the Gram matrix in the following way. It is the coordinate vector of U transposed multiplied by the matrix GB multiplied by the coordinate vectors of V, where UB and VB are the coordinates vector of U and V. What is the coordinate vectors? The scalars in the linear combinations of U and V as linear combinations of the elements of the basis B. Why is that so? It's not very long or hard proof, just a bit ugly because you write down all the sigmas I mean, U is some sigma A1, V1, A2, V2, and V is some sigma B1, V1, B2, V2. And then you write down explicitly all the stuff and eventually conclude that you get U and V. It's not very important, but it is something I wanted to say. And again, I don't think we will use it explicitly. We prove it explicitly, but we may use it in lectures to come, so it's good to write it down here. Okay. Any questions about our beautiful linear algebra 2?
Yeah.
Yeah.
Why did we learn about those three random, hang on, the inequalities? Like they just seem so random. Just to like throw that out.
First of all, Bessel is proving Cauchy-Schwarz, which proving that triangle inequality, which was already mentioned in previous lectures. So I wanted to give you not a complete, but more ordered mathematical proof. I mean, we have Bessel, which is right by Pythagoras, which you already proved in lecture number 9, I think. And Bessel gives us Cauchy-Schwarz, which gives us a triangle inequality. So first of all, we show them in order to fill up some holes in proofs we didn't prove in previous lectures. And secondly, we may use them in future material, so it's good to have them right now.
Okay.
Any other questions? Okay, so we can finish this class, rest a little bit, and half an hour from now, we have our little infi. We are, in situation is bad, yeah, but we march forward, yeah, we are close to the finish line.